We're examining the capacitive MEMS accelerometers, and we're looking at the data integrity problem of accelerometers. So this accelerometer contains a mass spring system. That is, we have this movable mass being attached to the fixed portion of the accelerometer with some sort of spring. When the sensor or accelerometer is exposed under motion, the movable portion, the movable mass, will move accordingly. The displacement is then converted into electrical signals, and the signal is then amplified and optionally going through a low-pass filter and then digitized. Now, what we've managed to do is basically control the measurement of accelerometers. That is, we let sensor to output any chosen measurement that does not reflect the real motion. Essentially, we utilize the following observations. Acoustic disturbance can also cause displacement of this movable mass inside accelerometers. Acoustic signals are mechanical waves. When we apply them to accelerometers, the movable portion will move accordingly. The displacement is kind of maximized, can be easily stimulated when the acoustic signal is at the resonant frequency of this mass spring system. And as a result, the electrical signals can be created either by motion or acoustic signals. Now, utilizing these observation, we managed to create two types of attacks. One is output biasing attacks, the other is output control attacks. With output biasing attacks, we utilize the phenomena of signal aliasing. So basically, in order to sample the correct signal, in order to avoid misinterpreting so for output biasing attacks, we utilize the signal aliasing phenomena. So according to the sampling theory, the sampling rate has to be at least twice of the maximum frequency of these analog signals. Now, when the sampling rate is inadequate, is lower than 2 times of the maximum frequency of the analog signals, and then the digitized signal no longer match with the analog signal. So you can imagine that if we sample this sine wave at the peak, every time the sampling point happened to be the peak of a sine wave, and then we will get this DC bias. So this attack utilizing this effect, we try to control where the sample point is so that the digitized signal will have this DC bias or DC offset. Now, we can use 2 ways to control how much DC output we want to create. One is using the amplitude modulation, the other using phase modulation. So with the amplitude modulation, we basically send a louder acoustic when we want the output to be louder. With the phase modulation, we control where the sampling point is, whether it's on the peak or on the valley, and then control the output of the accelerometers. For output control attacks, we utilize another phenomenon that's called signal clipping. So when the analog electrical signal goes through the first stage, an amplifier, normally the signal will be amplified properly. But if the original electrical signal is too loud, and it's louder than what this amplifier can take, then the output of the amplifier will have this clipped signal. So you can imagine this is like a big truck wants to go through a narrow tunnel. And in order for the truck to go through this narrow tunnel, the truck has to be chopped off. Same thing with signal clipping. So now with output control attacks, we send a really loud acoustic signal causing a large electrical signal. And this electrical signal is larger than what the amplifier can expect. And then the signal clipping happens. Now, according to the internal structure of this amplifier, the clipping does not happen symmetrically. It happens asymmetrically, which means the output signal tend to have this DC offset. As a result, we can control the output of the accelerometers.